lecture for a little bit. Again, we're going over this just to make sure everybody's on the same page as to how to do these things, just in case you didn't go into a lot of detail in Chem 50 about this stuff before we get into the real sort of chapter. So last time we left off here, sort of talking about how to balance these redox reactions in either acidic or basic conditions. We went through the basic steps, which are, I would obviously recommend, as we did there in this one, to identify what is being oxidized, what is being reduced. Once you do, you want to split it off into its half reactions. You want to then balance all the elements except for oxygen and hydrogen. Just like a normal equation, you use a coefficient to do so. Once you're done with all those, you then want to move to oxygen. And to balance oxygen in this method, we do use water, as we saw. And you would add water to whichever side needs the oxygen. Now, again, as we talked about, because you're adding water, you are also adding, in addition to the oxygen, you're adding more hydrogen. So for every water that you add to one side, you need to balance out the hydrogen by adding H pluses to the other side. And you would need to add 2 H pluses for every water that you do add to one side, and that would go to the other side. Once you're done, basically balance out the hydrogen and oxygen. And as I mentioned before, if you did run into sort of a situation where maybe, you were starting to balance in a half reaction, and maybe it had something like this, where you're also kind of starting with unbalanced numbers of hydrogen, you can just simply add an H plus to the other side and continue on normally, and that will make sure you have the right number of hydrogens as well. So you do want to watch that. It says sometimes it does pop into these that in a half reaction, maybe you are starting with more hydrogens on one side than the other. So at some point, you do need to take that into account to make sure that all the hydrogens do balance in that case. Now, once we've done that, and obviously we've done the hydrogens, the oxygens, the next thing you want to do is balance out, as we did, each half reaction in terms of its charge. And the way we do that is we add electrons. So you really need to add the electrons to whichever side needs the negative charge, that each side of the half reaction equals the same number. Again, it does not have to be 0 on both sides, but does need to be the same number, either positive number, negative number, on both sides of the arrow. Once you do that, you're ready to add them together. But like we saw here, if you do not have the same number of electrons in each of these half reactions, you do need to multiply the half reaction by a common number to get there. Sometimes it does require both half reactions to be multiplied by numbers. And sometimes it's just one. And sometimes you might not have to do it at all. You have the same number of electrons in each. Once you do that, you're going to combine everybody, cancel out the electrons, which should always completely cancel out. And basically what you would be left with at that point is the acidic equation, balanced in acidic conditions. As we talked about at the very end there, we know it because we see the H plus actually in the equation. It does need to be balanced like we kind of did on this one in two ways. It needs to be balanced like a normal equation, which means when you add up all of the elements on each side, you need to have the same number of elements on each side. So again, on this one, if we took hydrogen, chromium, oxygen, and iron, we got 14 there, 14 on the right. And again, we have 2 and 2, and 7 and 7, and 6 and 6. So just like a normal equation, everybody needs to be balanced. And secondly, they do need to be balanced in overall charge on each side. So if one of those things are not correct, then it's not probably correctly balanced. So those are the two things you should really always check at the end. Regular equation, same number of elements on each side, and also, again, overall charge on each side is the same. Any questions up to that point? So what we're going to talk about now is how you would balance this in basic conditions. And there's a couple different ways that you could kind of do it. But frankly, the easiest way to do it, if you do need to sort of balance it in basic conditions, is to just do what we just did, which is balance it in acidic conditions. And at the end, after you balance it in acidic conditions, you then can turn it into basic conditions. So that's probably the easiest way to do it. You can also kind of do this method before you add electrons up here. But if you do the method before you add electrons to make it basic, you have a lot more things to cancel out and stuff like that. So probably a greater chance of an error. So it's just better to kind of do it acidic and then turn it into basic. So if I recopy this equation on the next page, which hopefully I did correctly, we want to then basically kind of do this and turn it into basic. And when we turn into basic, we're going to add OH minus to each side. And the amount of OH minus that we're going to add is equal to the number of H pluses we have. So again, you just go through the balancing steps like we did. You balance it in acidic conditions. And then as we see here, we have a certain number of H pluses in our equation. And that is the exact amount of OH minus we want to add. So in this case, we would add 14 OH minuses to not one side, but both sides. So you do need to add it to basically both sides. Now, once we add it to both sides, you will obviously have a side where there's H plus and OH minus. And H plus and OH minus come together to make water. Yeah. So on that side, you will actually combine the OH minuses and the H pluses to make water. Everything else will stay the same, obviously, except for the OH minuses you added to the other side. And usually at this point, when you combine to make water, you will also always have usually some water that you could reduce down. So if I look on the right-hand side, I got 7 waters. I look on the left-hand side, I got 14 waters. You can think of the arrow like an equal sign. You can subtract the 7 from the 14. So the 7 waters cancel, and that's going to leave me over here a net of 7 waters plus our Cr2O72 minus plus our 6 iron 2 goes to our 2 chromium plus our 6 iron 3 plus our 14 OH minuses. And at this point, you should now be balanced, hopefully, in basic conditions. So let's just make sure. We'll run through our elements here. We got hydrogen, oxygen, chromium, and iron. Left-hand side, I got 14 H's. Right-hand side, I got 14 H's. Left-hand side, I got 7 oxygens there, plus 7 more there is 14. And over here, I got 14. I got 2 chromiums there, 2 there. And it looks like 6 irons on the left and 6 on the right. So we're balanced in terms of elements. Overall charge, we got this guy is going to give us 0. This whole thing is going to give us a -2. And this whole thing is going to give us a +12. So that's basically +12 and -2 is a net +10 on the left-hand side. Going to the right-hand side, this guy here is going to give us a +6. This guy here will give us a +18. And this guy here will give us a -14. So +18 -14 is a net +4, +4 and +6 gives us a net +10 on the right-hand side. So it is balanced in basic conditions at this point. Once again, much like the acidic equation, I know this is basic because I do see OH minus in there. So I know that this is balanced in basic conditions. Any questions on that there? Oh. God. Well, then it's your turn, I guess. All right, let's do it here. Go through this one. It's the one we just did. All right, so why don't you give this one a go here? Balance this guy, and looks like basic conditions. I minus plus MnO4 minus goes to I2. MnO2. So balances in basic condition. Also, idea what is being oxidized, what is being reduced, the oxidizing agent and the reducing agent, in addition to balancing. All right, so take a few moments there, knock it out, see what you come up with. Okay, so let's take a look, see how you're progressing, and make sure you're on the right track. So again, I'm always start with figuring out what is going on in terms of who's being oxidized, who's being reduced. So when we look at oxidation states here, our I minus is going to be -1 as that's the charge. Here with the MnO4, which is our permanganate, we're going to go -2 there for the oxygen, going to give us a -8. It does need to equal a -1 overall, which means the Mn here is actually carrying a +7 charge to balance that out. +7 and -8 gives us the -1 charge. The I2 on the right-hand side is 0, as that's a diatomic molecule, so that is how it normally comes. And the MnO2 here, starting with the -2 on the oxygen, -4. This doesn't equal 0 as there's no charge, which means the Mn here is +4. Any questions on assigning the oxidation numbers here? Those are really helpful because, again, it will allow you to figure out what is going on if you're not sure. Again, you can use a number line if you want to do that. Our I minus is -1, which is over here. Which is there, and ending at 0, which means the I minus is going towards the positive side, which means this guy is going through oxidation. By default, that would mean that this guy is going through reduction. You could also do the Mn here. The Mn on the right-hand side is +7, which would be like here. And on the right-hand side is +4, which means it's actually moving in that direction, becoming more negative, and thus going through reduction. Question on that? That would mean now that we know what is being oxidized, what is being reduced, we could also identify our oxidizing agent and reducing agent. And remember, it's opposite of what's happening to that substance. So the I minus is being oxidized, which means it's actually going to be our reducing agent because it will lose electrons. It will cause the reduction of somebody else, which is why it's referred to as the reducing agent. The Mn here really, and the MnO4 minus is going through reduction, which means this is the oxidizing agent. And it's going to accept those electrons that are going to be lost by the I and can cause the I to be oxidized, which is why it's the oxidizing agent. Any questions on that there? All right, now that we got everything kind of straightened out in terms of what's going on, we could get into the balancing part. This part, straightforward. We want to just match up elements, basically. So I minus and I2 in one half reaction. And then obviously this guy's got some Mn in it in one and some Mn in the other. So we already sort of identified this as our oxidation half reaction and our reduction half reaction. All right, after we split it off, first rule is we're balancing everybody besides hydrogen and oxygen, which in this case, we do need to put a 2 there for the I to make sure we have 2 on each side. On the bottom, we'd be looking at the Mn, and there is just 1 on each side, so we don't have to worry about that. Once we've done that, we can now move to the oxygen part of the program here. And the top one, there is no oxygen, so there's no need for water to be added to the top half reaction. Bottom half, I got 4 oxygens here and only 2 here, which means bottom one, we will need 2 waters, which in turn will give us 4 H pluses so that everything is still balanced at that point. We are now ready to add our electrons. So again, we're just looking to balance out the overall charge here. So overall here, that's a -2, and overall here, that is a 0, which means this guy needs a couple of electrons, which will give you a -2 and -2 in that half reaction. On the right-hand side here, this guy's going to give us a +4. This entire thing here is a -1. That is a +3 overall. That is zilch and 0. So that is a 0. So it looks like perhaps in this case we will need 3 electrons. Once again, we do know when we add those 3 electrons, obviously here 3 negative and plus 3 gives us 0 on both sides. When we add those electrons, we did do it to the correct side, as this is our oxidation. So we did add electrons to the right-hand side. This is our reduction. We did add electrons to our left-hand side. Remember, you should never add them to the same side because they do need to cancel out completely when you're all said and done. At this point, we're ready to add, except here, as you could probably imagine, we do have different numbers of electrons in each half reaction, and we cannot add these together until they are the same. In this particular case, we will need to multiply both of them by a number. If you're not sure and they don't divide into each other, the numbers of electrons, just multiply them together. So 3 times 2 is 6. So 6 is kind of the goal number we're looking for. To get the top guy to 6, you're going to multiply by 3. To get the bottom guy to 6, we will multiply by 2. Obviously, if one electron divides into the other, you have a larger number, and dividing it into a whole number, you could just do that number as well. So rewriting this here, go below, I guess, 6I minuses goes to 3I2 and 6 electrons. Multiplying that 2 on the bottom one gives me 6 electrons plus 8 H pluses plus 2 MnO4 minus plus 2 MnO2 and 4 waters. And again, I just obviously multiply these numbers to everybody. Now, when I'm ready to add these together, we will get our electrons to completely cancel, which is always the goal here. So we're going to do that. Electrons will cancel. We'll take a look here, and that looks like everybody that's going to cancel. So we'll carry down here 8 H pluses plus 2 MnO4 minus plus 6I minus. Again, everybody on the left-hand side stays there. Everybody on the right-hand side stays on the right-hand side of the arrow. So I2 plus 2 MnO2 and 4 waters in this case. Once again, this would be the balanced equation here in acidic conditions. Any questions up to there? You could check yourself. It should be properly balanced. So we do have 8 hydrogens on the left and right, 2 Mns. We got 8 oxygens on the left. 4 and 4 is 8, and 6 I's on each side. Overall charge, that's a plus 8. A minus 2 is a plus 6, and a minus 6 is 0, and 0 on the right-hand side. So if we were doing acidic, we would be properly balanced at this point, and we see the H pluses, which tells us it is acidic. But in this particular one, we did want to do basic. So at this point, what we can do is just continue on. So obviously, we're going to continue on now and go basic here. So to do basic, we're just going to add OH minuses once again to both sides equal to the number of H pluses. So in this case, 8 OH minuses and 8 OH minuses. That's going to give us 8 waters, which will then reduce down to 4 waters. Yeah. So 4 waters plus 2 MnO4 minus plus 6I minus goes to 3I2 plus 2 MnO2 and 8 H minuses on that side. And again, we should still be balanced now in basic conditions because we do see OH minus. We got 8 hydrogens on the left and right. We got 8 and 4 is 12 oxygens. So 4 and 8 is 12 on the right. We got 2 Mns and 6 iodides. Overall charge on the left is a whopping -8 from these two guys, a -8. On the right-hand side, it is a -8 as everybody else is neutral. So we are balanced in this case. Any questions on those steps there? All right, one last one just to make sure. Let's do, let's do this one. In acidic conditions, same deal. Identify what's being oxidized, what's being reduced, and balance this guy up. Look and see how you're doing. So we'll start with oxidation numbers. So this is again our -2, which is our -14 equals -2 when it's overall charge. So that's our +12, but there are two of them. So 12 divided by 2 is a +6 there for the chromium, as we saw earlier. Oxygen here for oxalate, -2 -8 equals -2. So that's a +6 I need. But there's also two of them, so each one would be +3 in this case. That's going to be a +3, and here to our CO2 -2 -4, and that would then be a +4. So again, if we take a look at the chromium, it is going from +6, which would be over here, to +3, which is moving in a negative direction. So that is going to be the guy going through reduction. By default, this guy should go through oxidation. And that would mean in this case as well that that our reducing agent here would be the oxalate, and our oxidizing agent would be the dichromate. Any questions on oxidation states, identifying what's being oxidized, what's being reduced? Obviously here as well for the carbon in this case, you could have started at +3 and it ended at +4, which is again moving in the positive direction. Any questions on that there? All right, ready to balance here. So chromiums with chromiums here. So this and this. And then carbon with carbon here. All right, so we're going to balance everybody other than oxygen and hydrogen. We will need a 2 here for the chromium, and we will also, for the bottom one, need a 2 for the carbon in this case. We're then ready to add our oxygen, so 7 oxygens there means right-hand side will need 7 waters. Left-hand side will need 14 H pluses. Right-hand side here on the bottom has 4 oxygen and also 4 oxygen there, which means by putting that 2 in front, it actually fixed the oxygen for us, so we do not need to add water in this particular case. At this point, we can do our electrons, so that's going to be a +14. That's going to be a -2, which is going to net us a +12 on the left-hand side. Right-hand side, a +6, really, and a 0. This is our reduction in this case. We do need to add 6 electrons here, which will give us a -6 and a +12, +6 on the left to match the +6 on the right. Any questions on that there? Also, we did add it to the correct side. That's the reduction, which means that is the correct side for electrons to be added to in this case. Here, overall charge -2, overall charge 0. That's going to need a couple of electrons there to balance out the charge to -2 and -2 in this case. Any questions at that point? All right, so in this case, we need to add them together, and we need the same number of electrons. We have 6 in one and 2 in the other. So if you take the higher number, 6, and divide it by 2, you get 3, which is a whole number. So that is what you should do, which is multiply just the bottom here by 3. Now, if we do that, the top equation did not change. So we'll have 6 electrons plus 14 H pluses plus some dichromate, coming over to 2 Cr3 pluses and 7 waters. Bottom guy, we're going to go 3 of the C2O42 minus, gives us 6 of the CO2 plus 6 electrons, which I believe is what he's looking for here. So electrons will cancel. And that actually is everything, I think, here that will cancel. So we'll end up with 3 C2O42 minus plus 14 H pluses and Cr2O72 minus. On the right-hand side of the arrow, looks like where'd it go? There, 2 Cr3 plus and 7 waters in that case there. And I am missing a 6 CO2. There it is. All right, so we have 6 carbons on each side. We got 12 oxygens on each side, 14 hydrogens on each side, 2 chromiums. Overall charge here on the left-hand side is -6 plus 14 and -2. So that's going to give us a plus 6, I think, if I did that right. And that's going to give us a plus 6 over here. And we have actually, I'm sorry, 19 oxygens on each side, 12 and 7 on both sides as well. This is again balanced in acidic conditions as we see H plus in our equation. Any questions on how to balance redox reactions in acidic conditions, basic conditions, identifying what's being oxidized, reduced, oxidizing agents are reducing agents? Any questions on any of that there? Okay, so clearly that is a very important skill for really what this chapter is kind of about. And let's get into really what the actual chapter really is. Now that everybody has the same foundation, and that is galvanic cells. And galvanic cells are basically redox reactions that occur. And there's basically 2 parts to a traditional galvanic cell. There is the anode part, and at the anode location, that is where oxidation occurs. So at the anode part, electrons are lost. Electrons travel through the wire that connects to the other compartment. And in that compartment, that is what is known as the cathode. And that is where reduction basically occurs. So what is really happening in this particular case is somebody is losing electrons. And when something loses electrons and becomes an ion, they actually end up in the solution. So in this particular case, we have zinc. That is going to give up a couple of electrons for each of them. So the solid zinc is pretty much here on the solid part. When it loses electrons, it goes for a swim and becomes zinc with a +2 charge in that case. So it jumps out of the solid state, it goes for a swim and is swimming around. As those electrons come to the other side, we actually have copper-2 ions swimming around, and those electrons come through and join up with the copper-2 ions that's floating around. At that point, the copper-2 ions decide it's time to get out of the pool, and it jumps out of the liquid part and into the solid part over there. So again, we're actually making some ions on the left-hand side, and then we actually have these guys leaving the solution as ions and going basically solid. Almost they will plate onto the metal that is there as well. We have typically on both sides, the anode and the cathode, we have a solid electrode that is used. And in the solution, we have the same ion. So like this is zinc. In the solution, we would have zinc ions floating around. Just like this guy is copper, and we would have copper ions floating around in that solution. The other guy there, really, the sulfate in each of these cases, it's just a spectator ion. It's not much going on. It's just kind of hanging out and, you know, having a good time, I suppose. Again, here, our copper-2 will gain those 2 electrons and become solid copper on that side. So this is our anode. This is our cathode. Those electrons which go out through the wire can be used to do some type of work. Again, as I said earlier, pretty much like a battery. That's pretty much how it functions. Electrons go out through the wire. If you look in your battery compartment, you see little wires there where you put your batteries in, and it will actually work. You'll get a voltage, and as we'll talk about, typically speaking, positive voltage is good for a reaction to be spontaneous. Negative voltage, not so good, but if it's negative voltage, you can make it, as we'll talk about, into positive voltage by just switching everybody around, basically, and it'll become positive voltage. Similar to if you put your batteries in backwards, they don't work, right? Until you flip them around the right way, and then they actually work. So the reaction will be spontaneous as well. There's also a really important function here, or another part to a galvanic cell, and that is the salt bridge. And the salt bridge is usually a tube like this in a lot of cases. That tube has some type of electrolyte in it, like an ionic compound, like in this example here, potassium chloride. And usually you put some plugs in it so your electrolyte solution doesn't all fall out at once, but it's able to sort of migrate through the little cotton there to kind of escape if they need to. The salt bridge is what basically connects both sides and keeps this galvanic cell running efficiently and correctly without the galvanic cell kind of stopping. So you might be asking, why would the galvanic cell perhaps stop if you didn't have the salt bridge? So for example, in this case, what we see is on the, I'll draw it here maybe. Maybe I'll draw it there. I don't know. I'll draw it there, I think. So if we take this little galvanic cell that we're looking at here in this picture, and we have zinc over here, we have zinc with a +2, obviously a little voltage action happening to the other side, where we got copper in a beaker with copper 2, right? All right. So as this cell is running, right, this zinc is basically dropping out, right? And there's also sulfate in here. We'll use our spectator ion. We'll pop them in. So this zinc is dropping out, and we're creating a lot of zinc ions in here, right? As these electrons basically start to transfer this way, right? Now, what that's going to do on the left-hand side is build up a quite positive charge, right? And what happened on the left-hand or the right-hand side here is these electrons are coming in and it's taking out all the positive charge on the right-hand side. And that leaves only the sulfate over here, right? Basically. So this is making this side more negative. And how a galvanic cell works is there's a cell potential or difference in charge. Electrons are negatively charged, which means they are attracted to a more positive situation and not so much a negative situation, which means if you take your salt bridge out with no salt bridge, you just built up a super positive side over here, which is really problematic because your negative electrons are going to go, I'm happier over here. I don't need to go anywhere. I'm attracted to the positive side, which means your electrons are not going to run to the other side, and your galvanic cell is going to be pretty much garbage at that point and not really function correctly because you're building up all this positive side charge on one side where you don't need it. By the way, you're also building up quite a negative side here, which is not going to make the negative electrons want to head over there to the right-hand side because things with the same charge don't really want to be near each other. So without the salt bridge, what will happen is you actually build up the charges in those beakers, for example, wrongly here for your galvanic cell basically to continue to function. That's why when you look at the salt bridge here, which is potassium chloride, when you put that salt bridge in, what happens is when we pop that salt bridge in, You have potassium ions going this way, and you got chloride ions going this way. And that's because without the salt bridge, we start to build up positive charge. We now drop in some negative charge to counteract that buildup of positive charge. Our positive ion goes for a swim over here to counteract the buildup of the negative charge. And what that's going to do is keep the right sort of difference in charge that will allow the electrons to continuously go from the anode to the cathode. So the salt bridge is a really important function for this galvanic cell to work correctly. It allows basically no buildup of, or it stops really the wrong buildup of charge on the anode side and cathode side by funneling in these other positive charged ions and negatively charged ions. These are really just spectator ions of potassium chloride, but their function here is to keep the charges where they need to be to allow the electrons to continuously flow. Any questions on that there? All right, so if you have a galvanic cell rolling and you take out that salt bridge, you will see the voltage plummet at some point because, again, you're just going to stop the electrons from flowing from one side to the next. Overall, this is still a redox reaction, which basically, if we look at the zinc, it's going from 0 to +2, becoming more positive, going through oxidation. The copper is going from +2 to 0, becoming more negative, going through reduction in this case. This gives us our overall reaction that's taking place. It is our zinc plus our copper 2 going to our zinc with a +2 charge and our copper with no charge here in this case. Again, that's the overall reaction that's taking place. Now, as I mentioned, there is a difference in electrical potential between the anode and the cathode when you look at a galvanic cell, and that is sometimes referred to as the cell voltage. You could almost think of it as the cathode being a more positive sort of side that's going to want to drag those electrons basically over to its side. And that will kind of pull those electrons from one side to the next because the cathode a little bit more positive. So our cell voltage, a volt is 1 joule of work per coulomb of energy transferred. Coulomb is a unit of electrical charge, and a joule is obviously energy, and a volt. The cell voltage is also sometimes referred to as electromotive force, EMF, our cell potential, which is that kind of pull of those electrons. So frankly, if you're asking a question to calculate either the cell voltage, the EMF of the cell, or the cell potential, they're all pretty much asking you to calculate the voltage for that particular cell is usually what the question is really asking you to do. Now, this is basically a galvanic cell that you could build in the laboratory with beakers. You can kind of see it right there. That's your salt bridge that's gapping both sides there. The beaker's there to keep everything functioning correctly. Here we do have a positive voltage, which is good for a galvanic cell. There is sort of a shorthand that you will sometimes see for galvanic cells, and that is what is sometimes referred to as the cell diagram. And here we have zinc line, zinc with a +2 charge, 2 lines, copper with a +2 charge, and copper with no charge. This is the anode compartment. This is both parts of the anode, basically separated by one line. This is the cathode part of the galvanic cell, also separated by one line. The 2 lines represents the salt bridge. So you also sometimes see written in these concentrations like 1 molar. If it is a gas, you may see pressure written in like 1 atmosphere or something different if it's something different. So sometimes you'll see those things. How does this cell diagram relate to the equation, or how do you go from like the cell diagram to the equation, or the equation to the cell diagram? Pretty much in the cell diagram, it's like this, usually reactants, products, yeah. So zinc a reactant, zinc with a 2 plus a product, copper +2 reactant, copper no charge product. So that is typically how it's written in a cell diagram. and it's always, again, anode to cathode is always the orientation. Other things that you may see in there as well is sometimes there is no solid electrode that you could use. So maybe you're doing something with hydrogen gas, which clearly there is no hydrogen solid that you could use. So sometimes inert metals like platinum is used sometimes in place of like a solid piece that acts as the electrode. Sometimes graphite is used, or carbon is used as sort of again, sort of a solid version of that electrode if the electrode is a gas. So sometimes you'll see some other things written in there. You may see like another line and something written that may be some type of platinum wire that's used as a sort of electrode. So when we look at galvanic cells, one of the things that we look at is what is known as standard reduction potential. And standard reduction potential is sometimes abbreviated as the SRP, or coincidentally enough, the standard reduction potential. These are reactions that are going on that are reduction reactions when you see them, and we will see a table shortly of them, and they're all written as reduction reaction, which is why they're called standard reduction potential. If you write it the other way, it's sometimes referred to as standard oxidation potential as well. So when we look at this, once again, we have our zinc here as our anode, and I know it's our anode because in the cell diagram, that is my anode there, and that's my reactant and product. So reactant and product in the overall reaction when we add together. Here, this is my cathode part, and this is my reactant and product. So again, reactant and product when you look at the overall reaction. Here we do see hydrogen being used as an electrode on one side. And here to the solid version of hydrogen that we will use here is this inert metal, which is platinum. So we do see it included in the cell diagram. In addition, hydrogen is a gas, so we see a pressure listed as well. Zinc is a solution, so we do see a molarity listed here. So here the zinc is going once again from 0 to +2, becoming more positive and being oxidized. It is the hydrogen here that's going from +1 to 0 that is being reduced in this case. And again, if you went to the number line for hydrogen, starting at +1, which is here, and ending at 0, and becoming more negative, going through reduction is what's really taking place here. Now, how do we get some of these values, these standard reduction potential values? As I mentioned before, it is a big table of values. And much like in chemistry, when they maybe can't directly measure sort of everybody, they do have to pick somebody to use as a standard value to compare everybody to. And for standard reduction potentials, they use the hydrogen electrode as the standard. And that is why it's sometimes referred to as the standard hydrogen electrode, or the She is sometimes referred to for standard hydrogen electrode. They gave basically the standard hydrogen electrode a standard reduction potential of 0 volts. So they just kind of assigned that a value of 0 volts and used it to compare basically everybody else too. This is the SRP reaction here. We see the electrons on the reactant side, which means this is a reduction half reaction that we are seeing. The problem with SRPs in a sense is when you have a redox reaction, you don't just have a reduction reaction, but you also have an oxidation reaction, which means, as we'll talk about when you go to this table, half of the value that you have is incorrect based on the way that it is written and what's going on. So they assigned here for 1 molar and 1 atmosphere of pressures a standard value of 0 for SRP. So what that allows them to do is take the hydrogen electrode and frankly just hook it up with a bunch of other electrodes and make a galvanic cell and get the voltage. And from the hydrogen electrode 0 value, they're able to basically figure out the SRP values for all the other elements that you may have going on. And for example, here they hook up the hydrogen electrode with zinc, zinc being again our anode, and our hydrogen here being our cathode on this side. And they get a cell voltage of 0.76. You could calculate the cell voltage or the cell potential by using this equation, which is E of the cathode minus E of the anode. Now, what I'm going to say right now will probably not make sense for a few more slides, but if you use this equation, you should not change the sign of any value you find in the table. So if you go to the table and you look up the values for zinc and hydrogen, you should just leave the signs exactly the way you find them in the table, and you should subtract the two values. Now, if you want to be correct, one of the values that you would find in the table should actually be reversed, and it should be the oxidation reaction, and that will actually change the sign. And sometimes people will do this equation as E of the cell is equal to E of the cathode plus E of the anode. But here you change the sign. And here the equation changes the sign for you. So I will say this again as we get closer and we take a look at it, but I would choose one way and kind of stick with it. Don't kind of mix and match, because then you'll add and you'll change the sign. You don't want to change the sign or not. So in this particular case, for example, the SRP for zinc would be this reaction. And it has an SRP value of minus 0.76 volts. Now, if I did not want the reduction reaction, which is clearly what I got going on here in this equation the way it's written, but in my case, maybe the zinc is actually being oxidized. That would be this reaction, which is just the top one reversed. And when you take one of these SRP reactions and you reverse them, what you do is technically the sign changes. So instead of being minus 0.76 volts, if you were doing the oxidation reaction, it would have an E value, it's sometimes referred to as standard oxidation potential, as plus 0.76. That is what I'm talking about here. If you decided to change the sign yourself, you should add those values. If you don't change the sign, that is what the minus is there for, to change it for you, because it should always be the anode one that you need to change the sign. So if you have a minus there, it will change the sign for you without you having to do it. So when you go to that table, technically speaking, one should change the sign. And if you want to change it yourself, you just add them. And if you want the equation to just change it for you, subtract the two values. Any questions on that there? So here, if we hook up, in this case, our standard hydrogen electrode with copper, we get a cell voltage of 0.34 volts. In this case, the hydrogen here is our anode, and it is the copper here that is our cathode. So this is a good demonstration that anything could be an anode and anything could be a cathode. It just depends on the combination you put together as to whether or not it will work good or not work good in terms of the galvanic cell. But anything has the potential there to be either a cathode or an anode. In this case, the hydrogen is going from 0 to +1, becoming more positive going through oxidation. Copper going from +2 to 0, becoming more negative and be going through reduction in this case. And again, here we can get our cell SRP value for copper 2, which is positive 0.34 volts. So this is a table of all those values there, which clearly you don't have to memorize. They will be given to you. But when we look at this table, pretty much all these reactions, they're all reduction reactions because we see equations on the reactant side. So these are all reduction reactions, which, as I mentioned a second ago, means that one of your reactions do need to be reversed, or one of the values that you find in that table does need to be reversed. So if we look at the sort of original one that we saw there, which was zinc plus copper 2, going to zinc plus copper solid, right? So solid, aqueous, and solid. So if we go to this table here and look up some of these values, we could find on this page, maybe copper, chromium, right there. So right up on top here is our copper. And the copper reaction looks like this. And the E there is positive 3.34 volts. Now, if we find our zinc, is my zinc on this page or the previous page? I feel like it's previous, perhaps. Let me go back. There's my zinc. There it is. There's my zinc. And there's the zinc, as we just saw there, going to be minus 0.76. So if we look at the zinc reaction here, minus 0.76 volts. Now, when we look at this, as we saw before, our zinc is going from 0 to +2, which means it is being oxidized. Our copper is going from +2 to 0, which means it's being reduced. Since these are both reduction reactions, technically speaking, the only one that is correctly written is our copper that's being reduced. Our zinc one actually needs to be reversed, so that will show the opposite. So if I take my copper and leave it alone, and since I left it alone, the E will be 0.34 volts. I flip my zinc to look like this, which is actually my oxidation reaction. When I do that, technically speaking, the reaction I just wrote, which is the oxidation reaction, should have an E value of positive 0.76 volts. I would change the sign. So if I added these together, the electrons here would cancel, and it would give me my overall reaction of copper plus zinc goes to zinc plus copper. Now, if I wanted to calculate the E of the cell here, in this particular case, because I already changed the sign, I would want to add these values together and not subtract. So that will give me 0.34 volts plus a 0.76 volts, right? And if we add that together, we're going to get some good voltage there of 1.1 volts. So that is what I'm talking about, that if you decide to flip the sign yourself, which is perfectly fine, and that's how some people are taught, you should flip the sign, just add them together. You should add them. Now, if you don't want to bother with flipping the sign and really you come across a question which is just simply asking you, what is the cell voltage, right? You don't have to actually write the equations or anything like that. You just want to know what the cell voltage is. You can just take the values that you would find in the table, and you can use the subtracting version of that, which is, again, E of the cell is E of the cathode minus E of the anode. And if I just want to know the voltage, I know that this guy's my cathode, 0.34 volts, minus my anode, which is minus 0.76 volts. Minus turns that into a positive, and you end up with 1.1 volts as well. So if you just want to figure out the cell voltage, you're not really interested in writing the balance equations, and that's really your goal, is just to figure out the cell voltage, just go from the table, take the numbers, leave the signs the way they are. All you have to figure out is what's your cathode, what's your anode, and you can subtract the two values. The subtraction will always change the anode one, which is the one that needs to be flipped, into the correct sign. If you are technically writing out all the equations and want to write the correct E values for your anode one, you should flip the sign and show the correct E value. And if you do flip the sign, you should add. So if you don't want to flip the sign, subtract. If you change the sign, add. Don't do both. Yeah, don't change the sign and then add, because I think you undid what you were supposed to do in that case. Any questions on that part of it there? All right. So a couple other things, as we just saw there, that can happen with these values that you look up in these tables. Here's another table, which clearly you can see all those numbers. Probably not, even if I blew it up, I don't even think you can see them. But when you do write an E value for an equation, though, it should be the value specifically for that equation. So if you were asked to write the oxidation or the anode half reaction, and what is the E value that goes with it, for our example that we just did, which was our zinc, I think. And if you're asked to write the proper equation with the proper E value, then technically in this situation for zinc, that is the equation that you should write with the positive 0.76 volts. If the zinc was a cathode, then clearly that would be the correct equation and correct E value to write it. So technically, when you see an E value, it should be specifically for how the equation is written, whether it's the oxidation or reduction. It should have the correct sign technically for the E value. Now, how do you know what is going to be your anode and what's going to be your cathode? So there is a rule that you could follow, and you could use the SRP values to help you make that decision. If you are not given any information about how the reaction is occurring, so if you're not given an overall equation, if you're not told, hey, this is reacting with this or anything of that nature, and they just simply said, hey, you built a galvanic cell out of these two things. So you just use these two things to build a galvanic cell. The one that should be your cathode is the more positive E value that you would find in that table. So the more positive E value is the greater tendency of that substance to be reduced, and the guy that gets reduced is the cathode. So if you're not given any information about how that galvanic cell works, you go with the more positive one should be your cathode. Obviously, in that case, the more negative one should be your anode. By the way, if you are given an overall equation, are told in words how the reaction is happening, you should actually look at the equation and figure out who's being oxidized, who's being reduced, and then that will tell you what is the anode and what is the cathode. So you only use the more positive one if you're really not given any information about how that reaction is happening. The half reactions are reversible. So if you take any of the reactions in that table and you reverse it like I just did there with zinc, the sign will change. So the sign will change. If it's positive, it'll become negative. If it's negative, it'll become positive. The other thing that's important with these E values is, as we saw when we were balancing these redox reactions, sometimes you do need to multiply a half reaction by a number, like a 2 or a 3, like we did earlier. When you do that, it will have no effect on the E value. So if you needed to multiply that zinc half reaction by like 3, you would not multiply the E value. So you don't multiply the E value by any type of coefficient that you need to do. Any questions on that there? All right, so let's take a look at one here, and why don't you do a couple things? What is the overall reaction? Why don't we write that as well? What is the anode? What is the cathode here? And what is the basically cell voltage? Yeah. All right. These are the SRP reactions and values you could get from that table. So see what you come up with in this case. So we want to know what is the cell voltage, basically the cathode, the anode, in a cell that's made by taking a cadmium electrode and 1 molar cadmium nitrate and a chromium electrode in a 1 molar chromium 3 nitrate. In this case, we're basically making a galvanic cell out of cadmium and chromium. That's sort of all the information they gave us, other than a couple other important things. Each of these concentrations are 1 molar, which means it is standard conditions, and that's a good thing to know. But it really doesn't tell us which one's which. So we can use, obviously, our equation, which is E of the cell is equal to E of the cathode minus E of the anode. In this case, because they didn't really tell us what's going on, we want the one that's more positive, which they're both negative, but out of the two negatives, this guy here should be the more positive one, as it's closer to 0, I'd imagine, right? So that makes it more positive. So this should be our cathode because of that, and this should be our anode in that case. Any questions on that there? Since the cathode is the one that is being reduced, that means that this equation is actually written correctly. Since this is the anode that's being oxidized, it means that this equation technically is written backwards. So since we do want the overall reaction here that I added on, we would reverse the bottom equation and make it into a oxidation reaction in this case. And when I flip that around, what happens to the E value here is it becomes now positive 0.74 volts. And if I wanted to now add, I'm just going to kind of put a little line through this one since I rewrote it. If I want to add my cathode reaction with my anode reaction, since it is still a redox reaction, before you could add these half reactions together, the electrons need to be the same number, right? So they're obviously not the same number here. Common number between those two is 6. So we're going to multiply the top guy by 3 and the bottom guy there by 2. So if I do that to get the balance equation, on the top there, we would have 3 of the CD2 pluses plus 6 electrons goes to 3 of the cadmium solids. Now, because I multiplied this by 3, once again, that has no effect on the E value. So we're not going to multiply the E value there by 3. I'm going to multiply the bottom guy by 2, gives me 2 the CR, goes to 2 the CR3 plus, and 6 electrons. Once again here, although I did change the sign, which I might have needed to do, I am not going to multiply it there. That means I could add these together. Electrons, just like a normal redox reaction, should always cancel out completely. And that will leave us our 3 cadmiums plus our 2 chromiums. Goes to our 3 cadmiums and our 2 chromiums. First off, any question on identifying cathode, anode, overall balanced equation? All right. Now it comes to really what the original question was asking, which is, what's the cell voltage is really what the original question was asking. Now, if I want E of the cell here, because in this case, I actually did change the sign, I would want to add, which would be in this case minus 0.4 volts plus a 0.74 volts, going to give us there 0.36 volts in this case. Now, if this was this original question where I didn't add on all the other stuff to do, and it really just wanted the cell voltage, once I identified what was my cathode and anode, I could have went right into the original equation there with the subtraction, where I went minus 0.4 volts minus a minus 0.74 volts. Once again, that's going to change the sign for me, and it will give me my 0.36 volts. So if you were answering the original question the way it was written, and that's really all you want to know, what's the cell voltage, and you could identify cathode and anode, you could just pop it in and subtract it. Don't change the sign. But if you want to change the sign, there's nothing wrong with that. You could just change it and add. Once again, I would pick one way and stick with it and not bounce back and forth, so you don't mess it up by changing the sign and adding them. Any question on that there? By the way, positive voltage is pretty good on this one, yes. So negative voltage not so good in a galvanic cell. Any questions on that there? All right, so that is enough torch